A circular loop is in a region of constant magnetic field pointed perpendicular to the plane of the loop into the page in our picture, and the magnitude of the magnetic field is equal to 0.85 Tesla. The loop circumference is decreasing. Its initial circumference is 210 centimeters and it's decreasing at a rate of 17 centimeters per second. The question is, what is the value of the induced EMF at t equals 6 seconds, meaning 6 seconds after the circumference of the loop has started decreasing. Let's apply Faraday's law. The magnitude of the EMF is equal to the time derivative of the magnetic flux being equal to B times A times cosine 0. B is the uniform magnetic field magnitude. A is the area of the circular loop. Why do we have cosine 0? Because the angle between the magnetic field vector and the area vector, which is perpendicular to the area by definition, is equal to 0, and cosine 0 is 1. So B is constant. We can pull it out of the derivative, but A is changing, right? Because the circumference is changing, so the area of the circular loop is changing. So the EMF's magnitude is equal to B times dA dt. Now, the rate at which the area is changing is not directly given. Instead, we know the rate at which the circumference is changing. So let's find the connection between the two. Based on the rate at which the circumference is changing, what is the rate at which the area of the loop is changing? The circumference of the loop can be expressed as 2 pi r, where r is the radius of the loop, and its area can be expressed as pi r squared. Now we can connect the area to the circumference in the following way. The area is equal to c squared divided by 4 pi. Imagine squaring c. You get 4 pi squared r squared, but we want pi r squared. So we divide by 4 pi to get the area. Now let's take the derivative of both sides with respect to time. On the left hand side we get dA dt equal to, on the right hand side, what do we have? We have a constant 1 over 4 pi. That one remains as is. And then we have c squared. The time derivative of c squared will be 2 times c times dc dt, like so. So we know what dc dt is. That's the time rate of change of the circumference, 17 centimeters per second. And we also need to multiply that by c, the value of the circumference at that moment at t equals 6 seconds. And then we'll have an overall factor of 1 over 2 pi to get the time, the rate of change of the area at that moment. Now let's substitute this result in our Faraday's law equation and calculate. Again, remember the EMF, induced EMF, is not constant. It changes with time because dA dt is not constant. And so we are calculating the value of the EMF at t equals 6 seconds. So we need to multiply B divided by 2 pi dc dt by C, the value of the circumference at t equals 6 seconds. The rest is constant though. So B is constant, dc dt is constant, the rate at which the circumference is changing, but the value of the circumference is not constant. So we need to substitute the value of C when t equals 6 seconds. We can calculate the value of the circumference at t equals 6 seconds in the following way. We know that the circumference is decreasing at a constant rate, so we can set up a function like so. The circumference equals the initial value minus the rate at which it's changing times t, because each second it's changing by 17 centimeters. So we just subtract 17 centimeters per second times 6 seconds from the initial value of the circumference, and we get 108 centimeters for the value of the circumference at t equals 6 seconds. Substituting the numerical values and keeping two significant figures, we get 25 millivolts for the induced EMF. Now let's determine the direction of the induced current using Lenz's law. Initially the flux through the loop is into the page, and the loop's area is decreasing. So the flux into the page is decreasing. The response of the loop to that will be to try to increase that flux or undo that change, or compensate for the loss of the flux that is being, decreasing. And it will try to create a magnetic field into the page, because the flux into the page is decreasing and the loop wants to restore the initial state. It will create some extra magnetic field into the page. That's the induced magnetic field. Now, in order to create magnetic field into the page, we need a current in the clockwise direction. How do we know that? We use the right hand rule. Align your thumb in the direction of the induced field, which is into the page. The curling direction of your fingers will show the direction of the induced current, which is clockwise.